Have you ever wondered why the triangle inequality is true? So if you don't know about the triangle inequality, it basically states that given a triangle, you can pick any two sides of the triangle, add their lengths up. The result of the addition is always going to be larger than the remaining side. Okay? Now, why is it true? I mean, it's a pretty strong statement, right? It does not restrict your choice of the two sides, right? You can pick any two sides, you add them up, it's always going to be larger than the remaining side. So, it's a very strong statement. So why is it true? Well, let's see. So let's draw up a triangle, right? And I've drawn this triangle in such a way that it's very clear which side is the longest side, which side is the second longest, and which side is the shortest side, right? So just by looking, we can establish that A is the longest side, B is the second longest, and C is the shortest side. Now, if I were to ask you whether or not A plus B is larger than C, would you agree? Well, I mean, just looking at this picture, it's pretty clear, because, you can directly see that, A plus B is going to be larger than C. But can you be a little bit more, can you give a bit more evidence, right? So, how do you prove that? Well, what you can see is that, A is already the longest side, right? So, by itself, A is already larger than C, right? So if A is larger than C, then A plus something is still going to be larger than C, right? It doesn't matter what that something is, right? It could be 1, it could be 2, it could be B, right? It doesn't really matter. But A plus something is going to be larger than C because, A by itself is already larger than C, right? It's sort of like saying, if I'm taller than my friend, then when I stand on a chair, I'm still going to be taller than my friend, right? Because, by myself, without the chair, I'm already taller than my friend, right? So it's the exact same logic, right? Now, what about A plus C? Can you prove that A plus C is larger than B? Again, using the same logic, by itself, A is already larger than B. So A plus something, whatever that something is, still that the result of the addition is still going to be larger than B, right? Because by itself, A is already larger than B. So using the exact same logic, we can prove two statements already. Okay. Now what about B plus C, right? The triangle inequality states that B plus C is going to be larger than A. But how do you prove it? You can't use the same logic that we've been using to prove the previous two inequalities. So yeah, it gets a little bit more difficult, but I think it's not too difficult, okay? So let's see how we can prove this final inequality. So our goal is to prove that B plus C is larger than A. So again, same triangle. However, we're going to draw a height from the top vertex down to A, right? So the height of each triangle is always going to be, it's always going to form a right angle with the base. So as you can see here, A is the base and there's a right angle there. And what happens is it splits the base into two parts. So I'll just call it A1 and A2, right? And what happens is now there are two sub-triangles, right? There's the left subtriangle and the right subtriangle. So let's work on the left subtriangle first. What we can do is we can just use the most famous the most famous theorem of all time in the realm of triangles, I suppose. That is the Pythagorean theorem, right? So a1 squared plus h squared is going to be c squared, right? Because c here is the hypotenuse, right? And from there, we can establish that a1 squared is less than c squared, right? Because a1 squared plus h squared equals c squared. That means that in order for a1 squared to reach c squared, it needs something to be added to it, right? So that implies that a1 squared is going to be less than c squared, right? Because in order to reach c squared, it needs something to be added to it, right? So that's the logic there. So we can establish that a1 squared is less than c squared, which implies that a1 is less than c. So we basically just got rid of the squares, right? So that's the result that we've obtained from the left triangle. Well, if we use the Pythagorean theorem on the left triangle, why not use it on the right triangle, right? So that's what we're going to do. So we're going to use the same renowned theorem on the right subtriangle. And using the exact same logic, we can arrive to the conclusion that A2 is less than B, right? Now, can you tell me, okay, just from these two results, can you say anything about the sum A1 plus A2? Well, the sum A1 plus A2 is going to be less than C plus B. And why is that? Right? Some people like to think of it as adding two sides of inequality, two inequalities. So we have the first inequality, A1 is less than C. Then we have the second inequality, A2 is less than B, right? So we add them up side by side, and you would get this inequality right here. You can think of it as that, right? Adding up side by side, or you can think of it as, the term A1 plus A2, right? Well, A1 is less than C, right? So A2 is less than B, right? So surely the sum is going to be less than C plus B, right? You can also think of it that way, right? Okay, now, what do you realize about this inequality? Well, it's very close to our goal inequality, right? Our goal inequality states that B plus C is bigger than A, and this one here, it's B plus C is bigger than A1 plus A2, right? So we're missing the plain A term, right? If we just had the plain A term in this inequality, we would be done, right? But we don't. So we have to introduce the plain A term into this inequality somehow. And that's actually pretty easy, because from this picture, we can clearly see that a1 plus a2 is just a, right? Because h split a into a1 and a2, so that means that a1 plus a2 is just a, and boom, we got our goal inequality, right? So a is less than b plus c, and then we can just swap the two sides. B plus c is bigger than a, right? And we've obtained our goal. So that concludes the proof of the the triangle inequality. Now I have a bonus question for you, right? Can you prove this theorem? The sum of the two longest sides is always at least twice the shortest side. Okay. I mean, this is a very interesting, theorem. Again, just, try your best, give it a go. I think even if you can't do it, you will still learn something from it, right? It uses the exact same tricks we used in this slide, namely the trick of adding two inequalities together side by side. So you will use that to prove this theorem as well. I'll wish you the best of luck, and thanks for watching.